Come on in, everyone. Look, more people. All right. Trying to get my notebook ready, everybody. It's about time to start, but I want to go ahead and give y'all a little bit of time while I'm doing this. Yeah, please do chat me your first and last name and ask me any questions you might have while I'm trying to get this note page worked out. So today's the 9th. Yes, that's always comes in handy to know what day it is. Feel like a smart person for the whole day. And that's the 9th. We got that done. Now I'll go back here, make a copy of it. All right. No one has asked any questions yet, but I'll give you one more chance. Anybody have any questions before we get started? All right. I hadn't made this announcement yet either to my memory. My intent is next week we'll have another online test. I'll probably open it Monday. In fact, I might even open up two of them next week. And that should be the last two online tests. Uh, the first one's going to be due not this coming Sunday, but the Sunday thereafter. That should be the next online test. The other one might very well be till the following weekend or something like that, but I'll probably give it a little earlier. That's why I just want to give y'all extra time on it. And the following week there should be another face-to-face test, not an online test, but a face-to-face test. And then, of course, the way the final exam was scheduled, I'm looking at it right now. I'm trying to remember on the syllabus. I think the last day of class is May 2nd. And if that's the case, if I'm remembering correctly, that May 1st or May 2nd is the second day of class, is the last day of class, then your final should occur on April 28th, and April 30th would be my last day that I allow people to actually take it because I normally set the final exam to be on the next to the last day of class, just in case anything messes up. I still have the extra day to work on, but either way, it would be the 28th if May 1st or May 2nd is it. Actually, if May, yeah, if May 1st or May 2nd is the last day of the semester, then the 28th of April would be the actual final exam day, and the 30th would be the extra day I'd have for that. So that's what I'm shooting for. But as I said, next week you'll have another online test that'll be due on the 20th. And then the following week you'll have a face-to-face test and probably another online test that would be due on the 27th. And then the final exam would actually be due the more than likely would be done on the 28th. I will have, just like I did last time, I'll have a time from like 8 in the morning, 9 in the morning, 10 in the morning, 11, noon, 1, and 2. Those will all be time periods where you could actually start the exam if you want me to proctor for you. Uh, that includes all my face-to-face students, but it also allows you guys those times. Otherwise, you'll have to find a proctor to do that. All the testing centers will do it for free, but you can find another proctor if necessary as well. So, anyways, I just wanted to get that out there. We are finishing up chapter 9 today, and I wanted to make sure you guys are ready for that. Let me kill this. So, the last thing we really had to do is I've already showed you sort of the trick of doing the one-dimensional collisions. Not only that, this weekend I made three. I only posted two of them, but I made three videos, and actually I've got two more I'm going to make. But two of them already been posted, and they are the details of exactly how you could go about uh, generically having a single solution for a head-on collision. If you look in your book on page, I want to say it was like 294 or something like that. Let me double check, or maybe it's 249. I can't remember. Let's see. At the bottom of page, let's see if this is it. That is not it. I'm looking on another page. Maybe it's 239. Yes, at the page 239, and I can't tell if this is the bottom of the previous page or the top of the next page, but there's an equation for VB prime and an equation for VA prime in your textbook, and it refers to problem 34. Basically, I worked a problem very much like that in those videos. So if you're already subscribed to my YouTube channel, you probably got to notice that those were posted. One's called a quick, actually, let me look at what I called it. One video is called A Quick Derivation General Solution for a Head-On Collision. That's the one I was just talking about for the general solution of a head-on collision. And before that is A Trick to Solve Head-On 1D Collision Problem. So there's a little process that you can do and just reuse that over and over. And that works fine. But if you want the actual generic expression that works for any initial conditions whatsoever, as long as the collision is elastic and head on, then the quick derivation gives you that complete solution. So definitely check that out. It's part of the lecture anyways, even though your book sort of chooses not to cover it. I chose to cover it just so you have a better understanding of it. Now that we've mentioned that, I want to go into the 2D collisions. We've already talked to some extent about, well, about elastic collisions, and I think you might have done, did you guys do ballistic pendulum in your 242 lab, or have you done it, or will you be doing it? Anybody know? We have a bank of labs that we use for our 242 course, and that's due this week. Okay, no problem, James. Uh, so the ballistic pendulum's another one, and there's a problem in your book on that. Let's start off with that one. I'll show you how to go about solving a ballistic pendulum problem, and we'll start from there. So, uh, derive, and I'm going to share my screen in a second. Hold on. I'll go ahead and do that now. Almost, if I don't say these things out loud, I might not do it by accident. So, here's the iPad screen coming up. All right, got another person just came in. So derive an expression for the muzzle velocity of a gun using the ballistic pendulum. So I'm going to do this a little different than we did in lab. So what I'm going to picture is this. Uh, we have a ceiling to which is affixed a big ballistic pendulum apparatus, which is hanging vertically and sitting perfectly still and has a mass of big M. And we have a projectile of mass little m moving with a velocity v0, which is the supposed muzzle velocity of the gun. And what's going to happen is this projectile is going to run into the hanging block. So this is a slightly later scene. it's going to embed in the hanging block and take off with the hanging block at some initial velocity, which I shall call just plain v. So this is sort of supposed to be the hole that the projectile left in the block. And now the mass is m plus big M, and it's moving horizontally with a velocity v. And then a little while later, what we have is the ballistic pendulum block. Oops. The ballistic pendulum block has now lifted up some height h. Okay. You'll notice this has different variables, for instance, than you did in your lab. But the main thing is we want a relationship between V0 and H. Okay. So first off, we'll start off with conservation of momentum. Anybody recall what is necessary in order for momentum to be conserved? No one. You can type it on your chat if you so desire. But I'm asking anybody remember what necessary condition is must be true for momentum to be conserved. Okay, so we're going to assume it's true, and from that, I'm going to say P initial is just lowercase m v0, and then P final. This is the middle scene that we're looking at here. So P final would be equal to m plus big M times v, and I'll write this middle picture. Ooh. Evidently, I wanted to write the word middle, and evidently I wanted to write something different there. So middle scene. So now we can say P initial is equal to P final when momentum is conserved. That means that M V0 is equal to M plus M times V. Therefore, we can get that V is equal to M over M plus M times V0. Okay. Now, I asked a question and allowed everybody to type in their answer. Let's see. And no one gave me a correct answer. I will remind you that conservation of linear momentum comes from Newton's second law. Here it is. Newton's second law says the summation of the forces is equal to dp dt, and if the summation of the forces is equal to zero, then dp dt is equal to zero. And when you take the derivative of something and you get a zero, that means that something is a constant. And the fact that momentum is a constant is the very statement of conservation of momentum. So the shortest way of seeing under what conditions is linear momentum conserved is saying that the left-hand side of Newton's second law is zero, You can give it a few more words to make it a little more reasonable, and that would be the net external force acting on the system is zero. So that's what the answer is. So when someone asks you, under what conditions is linear momentum conserved, you say when the net external force on the system is zero. Okay, and this derivation that I did over here on the right hand edge, that is just my derivation of the fact that conservation of momentum is due to the summation of forces being equal to zero. Now I'm going to use conservation of mechanical energy. And I told you a couple different ways you could use that. In fact, the way your book generally does it is you could say delta U plus delta K is equal to zero. That's one way. Another way is you could say U initial plus K initial is equal to U final plus K final. And that would work as well. Or you can use my way, which is U initial plus K initial plus uh, work in is equal to U final plus K final plus E loss plus work out. All of those work as well. The main thing is once we've eliminated all the stuff that's not useful, we're only going to get basically that kinetic energy initial is equal to potential energy final. In other words, all the other stuff is zero. Therefore, we have 1/2 m plus big M v squared is equal to M plus big M G H. So that is an expression that relates the velocity of the projectile plus the block once it's been embedded in the block. That's the relationship of that velocity to the height h. But now we're going to use the equation we found above for v in terms of v0 and replace that. So now what I'm going to do is I'm going to say 1/2 m plus m. Now in the place of v, we're going to use this expression. So that's going to be m over m plus big M times v0, and all that's got to be squared, and all that's got to be equal to m plus big M times G times H. You can automatically see that this M plus M and this M plus M can cancel each other out, and you can continue with your algebra a little bit, and you'll see that I can multiply both sides by 2. That'll help, like that. And in so doing, now I'm going to have m squared. I don't like the looks of that too. M squared over m plus m squared times v0 squared is equal to 2 times G times H. So now I can solve for V0 squared by writing 2 times M plus M squared times G times H divided by M squared, or finally we can say V0 is equal to the square root of 2gh, but it's going to be times m plus m over m times the square root of 2gh. That's the result we're shooting for. So anybody have any questions about how we did that? I want to remind you that this is a situation where one moving object runs into another object that was sitting still, but now they're stuck together. When that happens, that type of collision is called a totally inelastic or completely inelastic. Sometimes people will just say the word inelastic, but I think that's a little of a misnomer because inelastic just means it's not elastic, which means kinetic energy is not conserved. When we're talking about two objects sticking together after their collision, we need to call that completely inelastic or something like that, totally inelastic. Either way, the totally inelastic is basically what they talked about in questions 3, 4, and 5 in the ballistic pendulum lab. So when you actually start working that ballistic pendulum lab, you'll get a better understanding. But it turns out there's a very specific formula for the change in kinetic energy divided by the initial kinetic energy when you have a completely inelastic collision. So that's something they're going to ask you to do in your lab. And hopefully, by seeing this derivation of the original equation, you might have a little bit of an idea how to go about calculating what you have to calculate to make that calculation, which is the initial kinetic energy, which notice the initial kinetic energy is just lowercase m 1/2 times lowercase m times v0 squared. And then the collision or the kinetic energy after the collision is 1/2 parenthesis m plus big M times v squared. So that's the final kinetic energy. What your book's going to, or what your lab manual is going to ask you to do is do the opposite of the change in kinetic energy. They're actually going to take the final kinetic energy. No, yeah, they're going to take the initial kinetic energy minus the final kinetic energy and then divide it by the initial kinetic energy. And you'll get an expression that's just related to the masses, M and big M and stuff like that. In that one, though, remember the big M corresponds to the total mass of the block plus the bullet, and the little m just depends on the mass of the bullet. So be advised when you're doing that lab, but this is how you do it in general, where you're treating the big M as the mass of the block that's hanging on the pendulum, and the little m is the mass of the projectile fired from the bullet. Anyone have any questions on that? Okay, so kinetic energy is conserved in elastic collisions. All we used here was conservation of linear momentum, and then we use conservation of mechanical energy, not kinetic energy. Okay, all right. That looks like no one has any questions. I don't see anything. Uh, let's go on now to the next part, which is talking about collisions. Well, I'll go ahead. Nah, I'm going to skip example 911 and let you do that on your own. So, uh, study example 9-11 on your own. As always, if it's a section that I cover, and generally I cover all of them unless they have an asterisk by the name. So any section that doesn't have an asterisk next to the name or subsection next to the name, then have an asterisk next to the subsection name, that is. Any of those sections I always cover, and when I cover, that means you're responsible for all the examples in it. This is one of those cases. I'm just pointing out to you that I'm not working it because it's literally just like an example I've already worked when we first started this with two train cars colliding. Now I'm going to go into two-dimensional collisions. So, uh, 2D collisions. Now, technically, your book calls this 2D and 3D, and in principle, you can make it a 3D collision. But if you're using two particles, uh, it's rare that you necessarily have to go into three dimensions, but you could. Okay, and I'm talking from the physics teaching world, not necessarily from the physics experimenting world. So that's why I said it that way. But what I want to show you is there's one really nice trick that you can use over and over again when you're solving a head-on, or excuse me, a 2D or 3D collision. And I want to show you that. So I'm going to draw a coordinate system for two projectiles that are going to collide, and I'm going to draw one sitting still, and that's going to seem a little odd, like you're only studying a very special case, but it turns out that that is not a special case because when we're working in atomic physics or any kind of collision, particle collision, stuff like that, we readily will jump to a coordinate system that's moving with one of the particles. So if you can take particle B, which is the one we're going to say is sitting at rest initially, if you can figure out what its speed is in your frame, then all you have to do is switch to a frame that's moving in the same direction as particle B with the same velocity as particle B, and then all these answers that I work out will come out correct. Okay, so that's why it's not a special case. It is, in fact, the most general case. So, what we're going to do is, for starters, we're going to put a little round mass at the origin. That's going to be MB. And there's going to be another round mass moving along the x-axis. This too is completely general because you can always align the direction of velocity parallel to the particle and make that direction also parallel to the x-axis. So that's what I've done here. I'm calling this, oops, I meant to write that in black. I'm calling this the x-axis and I'm calling this the y-axis. And then after the collision, what we're going to get is one of the particles is going to go this way so that now you'll have a particle with a velocity this way, and you'll have another particle with a velocity this way. Now this particle will be moving with a speed here. I'm going to call this particle MB and its velocity VB prime. I'm going to call this particle MA and its velocity VA prime. I'm going to say this angle is theta A prime and this angle is theta B prime. And I also have to include that this particle had a initial velocity and a mass given by MA and VA like that. Okay. This one, on the other hand, is a mass MB and VB is equal to 0. Okay. So that's the actual diagram of the collision. If we assume the right assumptions for the momentum to be conserved, anybody want to restate that now that I've told you what the answer was? Well, that's weird. Oh, I saw some weirdo walking up to my mailbox, and I'm looking out there like, who the crap's going in my mail? It's my wife. I wasn't recognize what she's wearing or anything. Anyways, so anybody have an answer? What under what conditions is momentum conserved? Please tell me now. Yes, very good. The net external force on the system is 0. That's exactly it. Good. I'm having a really hard time with this. My students in my classes, my face-to-face classes, and my online classes are not getting this, and I've asked them like several times. So I'm glad. Thank you, John. Appreciate that. All right, now we're going to take conservation of momentum. First off, I'm going to take it to be conservation of momentum in the x direction. And that's actually not too terribly hard to do. What we're going to see is P initial is just equal to MA VA. Now I'm saying in the x direction, so I don't actually have to do any vector symbols or anything like that because I've aligned the coordinate system that I use. In one sense, it's actually aligned such that it's moving at the exact same velocity as particle MB. And then in another sense, it's also set up such that the x-axis is exactly parallel to the initial velocity VA, so that it makes no angle with the x-axis. So that's the total momentum before the collision. After the collision, since we're treating the system as if it's both particles, it's going to be MA VA prime, and I'll put an X down there, meaning the X component, plus MB VB prime, and I'll put an X down there, meaning it's the X component. Now, if the hypotenuse of this velocity is VA prime, and then of course that's this one right here, and the hypotenuse of this velocity is VB prime, you can see that multiplying the VB prime times the cosine of theta B would give me the X component. And if I multiplied the VA prime times the cosine of theta A, that would give me, or theta A prime, that would give me the X component. So now I'm going to go ahead and set these two equal to each other, and that's going to give me MA VA prime equals MA VA prime cosine theta A prime plus MB VB prime cosine theta B prime. Okay, I'm going to call that equation one. That's conservation of momentum in the x direction. Now I'm going to do conservation of momentum in the y direction. So I should probably separate this so there won't be any confusion where things are starting. So the initial momentum in the y direction is actually zero because the only thing that's moving initially is just m sub a, and that's moving in the x direction, which has no y component. Okay. The momentum after the collision is actually equal to ma va prime, but we need the y component, plus mb VB prime, but we need the Y component. In this case, you can see by taking and multiplying VB prime by sine theta B prime, you get the Y component. And by multiplying VA prime by sine theta A prime, you get the Y component. So setting the two equal to each other, this actually allows us to get 0 is equal to MA VA prime sine theta A prime plus MB VB prime sine theta B prime. That is equation two. Now, that is just the two main parts for conservation of momentum. But if we also learn it's an elastic collision, so if the collision is elastic, then K initial is equal to K final. And this is more or less the case in just about every subatomic particle collision. So when you have subatomic particles, it's very unreasonable to think that there's going to be a lot of energy exchanging hands other than just the momentum and kinetic energy from collisions. Now, that being said, if the collisions don't happen fast enough, you could actually have, one particle trying to repel another particle because they're both the same charge, and then at the same time they're going to be attracted to each other because they both have mass because gravity. But if that doesn't take very long, then those forces and those should actually result in a minimal change in energy, so you can then assume it's roughly a elastic collision. But let me go ahead and write out the equation for an elastic collision. For an elastic collision, well, for starters, the initial kinetic energy is just equal to 1/2 m sub a v sub a squared, and then the final kinetic energy is 1/2 m sub a v a prime squared plus 1/2 m sub b VB prime squared. Now you can see there's a common factor of 1/2. I'm going to go ahead and multiply by 2 and set K initial equal to K final. So when I do that, I'll say K initial equals K final. And from that, I get MA VA squared is equal to MA VA prime squared plus MB VB prime squared. And this is going to be equation 3. Okay. Now, this doesn't really help you that much, but this is just the setup of the equations. These should be equations, these three equations you should be able to write down immediately just off the top of your head because you understand enough about vectors to find the x components and the y components, and you know the assumption is that the initial particle is the only one moving, that's ma, and it should be moving in the positive x direction. So you should be able to come up with these first two equations in the case of any collision in which the total external force is 0 acting on the system. But if you also include that the kinetic energy is conserved, that it's an elastic collision, then you should immediately be able to come up with this third equation. Now, the trick to this is what's followed. So I'm going to write this in green and say, here is the super helpful math trick. Okay. The super helpful math trick is 1 in equations 1, 2, 1 and 2. Let's do it that way. 1 and 2. Get all A stuff on left side and all B stuff on the right side of the equations. And then step 2, square each side. And then step 3, add the result from 1 to the result from 2 and use sine squared theta plus cosine squared theta is equal to 1. So that's the trick. Okay. When you do that, that'll eliminate so many variables and so many terms that the remaining part of the solution is usually fairly trivial. So let me demonstrate that. So 1 is going to become, if I pull MA, VA, that's already on the left-hand side, but now I got to pull the MA, VA prime cosine theta A prime to the left-hand side as well. So I'm going to say minus MA, VA prime cosine theta A prime. And then the right-hand side is just going to be MB, VB prime cosine theta B prime, like that. Now I'm going to square the equation. So when you square a binomial, remember it's the square of the first term, then you add to it 2 times the product of the two terms, and then you add to that the square of the last term. So that's going to give us MAVA squared minus 2MA squared, because it's MA times MA, times VA prime times cosine theta A prime. That's the middle term. Now I have to square the last term as well, so that'd be plus MA squared VA prime squared cosine squared theta A prime. And then that's equal to the right hand side, which is super easy. So that's MB squared VB prime squared cosine theta, or cosine squared theta B prime. So I'm going to call this equation 1 prime. That's a key. That's steps 1 and 2 already committed for equation 1. Now I got to do the same thing for equation 2, but you can see equation 2 is a lot easier because I'm just going to have one term on each side. So now I'm going to say equation 2, we're going to have negative MA VA prime sine theta A prime is equal to MB VB prime sine theta B prime. That's what happens when I get the A's on one side and the B's on the other. Now I've got to square both sides, and that's going to give me MA squared VA prime squared sine squared theta A prime is equal to MB squared VB prime squared sine squared theta B prime. This is equation 2 prime that we're going to make use of. Now I want to add 1 prime and 2 prime. So to do that, all I'm going to do is take the MA squared VA squared minus 2MA squared VA prime cosine theta A prime plus MA squared VA prime squared cosine squared theta A prime is equal to MB squared VB prime squared cosine squared theta B prime. Okay, so that's equation 1. Now or 1 prime. Now I'm going to take equation 2 prime, and I'm going to write it in a way that's most helpful. So I'm going to write the first term right here. That's MA VA prime squared sine squared theta A prime. And then on the other side, I got MB squared VB prime squared sine squared theta B prime. So you can see that when I add the terms that are lined up with each other, I can factor out the the MA squared VA prime squared, and I can also factor out the MB squared VB prime squared, and that's left with just the sine squared plus cosine squared for each of them. So that just becomes 1. So now if I add these two equations, I get MAVA, both of those are squared, minus 2MA squared VA prime cosine theta A prime. Now I'm adding the actual terms that could be added, and I'm getting plus MA squared VA prime squared times sine squared plus cosine squared. We know that's going to be 1. I didn't even take the time to write the argument. The same thing's going to happen on the other side. I'm going to get mb squared vb prime squared, and sine squared plus cosine squared comes out of that. And as I said, sine squared plus cosine squared is 1, and sine squared plus cosine squared is 1. So my ultimate result is ma squared va squared minus 2ma squared va prime cosine theta a prime plus MA prime squared is equal to MB squared, MA squared, VB prime squared. Okay, so this will be called equation 3, and it's sort of important. It's not important in the sense that you need to commit it to memory, but if you do this process a couple times, you'll commit it to memory. Okay. But now you've got that you can use. And notice the beauty of this. In general, we expect to not know VA prime, VB prime, and at least one of the angles, theta A prime, right? Sometimes we might know VA, but won't know VB prime, or excuse me, we won't know VA. Sometimes we can assume we know VA prime, but will not know VB prime, and we won't know theta A prime or theta B prime. That's another way you can solve it. But in all those scenarios, if you have 3 unknowns, it has to be elastic or you can't solve it. If it only has 2 unknowns, it need not be elastic, and these 2 equations should be enough. So now that I've had that and I've explained the process of how this goes together and what the kinetic energy being conserved gives us, we can go ahead and solve a problem. So the problem I'm going to solve is pretty much one that's in the book, and I'm going to say a pool ball uh, let's call that M sub A, is moving at 4.0 meters per second in the positive x direction when it runs into another identical pool ball whose mass should be m sub b. The 2 balls are observed to move off at 45 45 degrees to the positive x-axis so that theta A prime would equal positive 45 degrees and theta B prime is equal to negative 45 degrees. What are VA prime and VB prime? So that's the example we're trying to solve. Whoa. So there's example 2. Solution. In this case, we actually have the fact that all the masses are identical, so I can start off with my conservation of momentum equation for the x direction as just VA is equal to VA prime cosine theta A prime plus VB prime cosine theta B prime. Again, I'm going to do our trick, which is to get all the VAs on one side or the A's on one side and square it. So that's going to become VA squared minus 2VA VA prime cosine theta A prime plus VA prime squared cosine squared theta A prime is equal to VB prime squared cosine squared theta B prime, like that. Now, we already know that theta A and theta B are 45. Well, 45 and negative 45, but cosine's symmetric. So if you take the cosine of negative 45, you get the same thing as cosine of 45. And the cosine of 45 and the sine of 45 are both 1 over the square root of 2 or 2 over root, or excuse me, or root 2 over 2. Either one is acceptable. So I can go ahead and start plugging in the numbers that I know. So for instance, this is going to be 16.0 for the square of the first term. I'm going to leave the units off and sort of think about them in my head, but I'm just leaving them off because it's too much writing and it'll be too hard to fit in. Then I'm going to have minus 2 times 4.0 times VA prime times the square root of 2 over 2 is 0.707. Let me double check that. Yeah. So I'm going to say times 0.7071, and that's carrying my extra sig figs. Actually, it's carrying two extra sig figs. And then plus VA prime. Now, the square root of, or excuse me, 2 over, or square root of 2 over 2, when you square that, is just going to become 1/2. So in this case, I'm going to say 0.50 for that. And then this one's going to be VB prime squared times 0.50 for that as well. I can simplify a little bit by saying this will be 16. Oops. I can say this will be 16.0, 2 times 4 times 0.7071 gives me minus 5.6568 times VA prime. And I will say plus 0.50 times VA prime, whoa, times VA prime squared. That's supposed to be squared. I left off the square earlier. And then this side is going to be 0.50 VB prime squared, like that. So you can see right now I've got two unknowns, VA prime and VB prime, and this is basically the equivalent of equation 1 prime. Now I'm going to do the conservation of momentum in the y direction. Again, I'm making use of the fact that MA equals MB equals just plain M. So MA equals MB equals just M. That's why I have no masses in it. Now, if I look at equation 2 for the y component, what we're going to have in that case is no mass, but we'll still have VA prime sine squared theta A prime is equal to VB prime squared sine squared theta B prime. Now, we know that both of these result in 1/2. In other words, the sine of 45 degrees is equal to the square root of 2 over 2. When we square that, we're going to get 1/2. And the same thing happens here. This is the negative square root 2 over 2. But when you square it, it's still going to become 1/2. So we're seeing that VA prime times 1/2 is equal to VB prime times 1/2. So we can already reach the conclusion that VA prime is equal to VB prime. This is equivalent to 2 prime. Okay. Now that we have that, we can plug 2 prime into 1 prime. And what we're going to get now is 16.0 minus, whoa, just started writing out of nowhere. So 16.0 minus 5.657, that's carrying 2 extra sig figs, VA prime plus 0.50 VA prime squared is equal to 0.50. Now, since VA prime is equal to VB prime, I'm just going to replace this with VA prime squared, and automatically you can see that this term and this term cancel out because all I have to do is subtract zero point 0.5 VA squared from both sides, and that's going to give me 0 on both sides for that particular term. So now all I have is that 16.0 is equal to 5.657 VA prime. So VA prime is going to be equal to 16 divided by 5.657, and that gives me 2.828 meters per second is VA prime. But we also know VB prime is equal to 2.828 meters per second as well because they had to be identical. Any questions on that? So this one, they didn't tell us it was elastic, so I wasn't able to use equation 3, but I was able to use the nice little technique that we had, and hopefully y'all can understand how that was used. Anybody have any questions on that one? All right. Next, let's do an example 3. And this one says a proton is traveling at, let's say, 4.0 times 10 to the fifth meters per second when it collides elastically with another proton at rest. Again, it could really be at rest, or we just could be in a frame in which it's at rest. One proton leaves at, whoa, there it goes again, at an angle of 60 degrees above the positive x-axis. At what angle will the other proton leave? That's part of it. What will be the two velocities. Whoa, there it goes again. Speeds, let's say, after the collision. So there's our problem. Okay. This one's elastic, so we're actually going to make use of all of them, but they're both protons. So we can start off again with equation one, equation two, and equation three. This time we're actually using equation three, but we're going to go ahead and divide out the masses from the beginning. So we'll start off like this. Solution. What we're going to say is m time. Well, again, getting rid of the mass. Well, I guess I could leave it in there. I think it's best to just take it off from the beginning. Remember, it was originally it was MA times VA is equal to MA VA prime cosine theta A prime plus MB VB prime cosine theta B prime. But all of those M's cancel out. So now all I get is VA is equal to VA prime cosine theta A prime plus VB prime cosine theta B prime. Okay. I do know one of them is going to be 60 degrees, and of course the cosine of 60 degrees is 1/2, and the sine of 60 degrees is root 3 over 2. So I'll say sine 60 is equal to square root 3 over 2, and cosine 60 is equal to 1/2. We're going to make use of that, but now I've done the x component. I'm going to use our trick, which is get all the a's on one side and the b's on the other and then square it. So now I've got VA squared minus 2VA VA prime. Now, cosine, I'm going to go ahead and say theta A is the 60 degrees, and that's just going to be fine. So the cosine of 60 is 1/2, so I'm going to say times 1/2. So now I've got the product of the two terms, VA negative VA prime cosine theta A prime. And now I got to square the last term, which would be plus VA prime squared, and then 1/2 squared would be 1/4. So this is 0.25 right there. The right hand side is just going to be VB prime squared times cosine theta B prime squared. So I can simplify this a little bit more and write it as VA squared minus 2 times 4.0, because VA we actually know that's 2 times 4.0 times 10 to the fifth meters per second times 1/2. The 2 and the 1/2 essentially cancel each other out. So all I'm going to have now is just VA, which is 4.0 times 10 to the fifth times VA prime plus 0.25 VA prime squared is equal to VB prime squared cosine squared theta B prime. Okay, so this is the equivalent of equation 1 prime. Now I'm going to use equation 2. Equation 2 was 0 equals, and then we had the m times v times sine, that sort of stuff, and then we had to square it. So in this case, we're dividing through by the m, so I'm going to say VA prime sine theta A prime, which we know, plus VB prime sine theta B prime, which we don't know. When I square them, I'm going to get VA prime squared sine squared 60 degrees is equal to VB squared sine squared theta B prime. Okay. Now I know the sine of 60 is root 3 over 2, so when I square it, I should get 3/4. So this is going to be 0.75 VA prime squared is equal to VB prime squared sine squared theta B prime. This is the equivalent of equation 2 prime. Now if I add, so this is key here, add 1 prime and 2 prime, and that'll allow us to get rid of the theta B prime. So when I add them, what's going to happen is the left-hand side of equation 1 prime is going to be, oops, is going to be VA squared minus 4.0 times 10 to the fifth VA prime plus 0.25 VA prime squared is equal to VB prime squared cosine squared theta B prime. And I'm adding that to, in this case, I'm going to say 0.75 VA prime squared is equal to VB prime squared sine squared theta B prime. So when I add these two equations, you see that I get VA squared, which I was already supposed to know. I should have written that in fact. Let's go ahead and do that now since I've been forgetting to do it. We already know VA prime. I don't know why I didn't put it in, but I didn't. So uh, this is going to be 4 times 10 to the fifth. 4 times 10 to the fifth squared. That's going to be 1.6 times 10 to the 11th. So I'm going to say 1.6 times 10 to the 11th minus 4.0 times 10 to the fifth VA prime plus 0.25. Oh, in this case, we're actually adding them. So 0.25 VA prime squared plus 0.75 VA prime squared just gives me VA prime squared. And the right-hand side just gives me VB prime squared because sine squared plus cosine squared is equal to 1. Does everybody follow how I got that? This is the equivalent of equation 3 that we found before. Now I'm going to make use of the kinematic, or excuse me, the conservation of kinetic energy. So conservation of kinetic energy is going to give me, remember the masses cancel out. So ma equals mb equals just plain m. So now I just have the squares of the velocities. If you want to look at the original expression, we're talking about this equation right here, but without the without the m's. So what we get here, and it's actually kind of nice and super helpful. I can tell you right now, for instance, that I know the angle theta b prime has to be 30 degrees. Actually, technically, it has to be negative 30 degrees because the two have to differ by 90 degrees whenever two identical particles collide collide elastically, because look at what happens to conservation of kinetic energy. We say VA squared, and actually I was writing in blue, so I need to stick with that. We say VA squared is equal to VA prime squared plus VB prime squared. What does that look like? Does anybody ever seen something that looks like VA squared equals VA prime squared plus VB prime squared? Anybody think that looks like something? Remember, we're talking about vectors here. VA is a vector, VA prime is a vector, VB prime is a vector, but their magnitudes are associated with each other like this by this equation. Can anybody tell me what this looks like, or does it look familiar at all? I will tell you that you can imagine something like this. This is vector VA. This is vector VA prime. And this is vector. I'm not drawing it quite well enough. Let's see. And in fact, I need to make this VA a little better. But the main thing is, and hopefully you're seeing what I'm doing now. And this vector is VB prime. And in fact, now do y'all recognize it? How about oh, there you go. Good job,
Making
John.
the assumption it's a right angle.
Yes, it's a right angle. In fact, if you have the magnitudes of three vectors and they add up as the square of one is equal to the sum of the squares of the other, we know that's a Pythagorean theorem as John typed in. So this tells you that the angle between VA prime and VB prime should be 90. So if VA prime is 60 degrees positive, then the VB prime has to be negative 30 degrees. That's how I know that immediately. And that's true anytime you have an elastic collision with two identical particles, one sitting still. Okay. The two angles have to add to give you 90 degrees because VA prime and VB prime will be different by 90 degrees. So, because of that, we can go ahead and get rid of VB prime. We can say VB prime squared is actually equal to VA squared minus VA prime squared, like that. And then we can call this equation 4. Oops. And we're going to plug 4 into the last equation we got, which was 3. When I do that, I'm going to get 1.6 times 10 to the 11th minus 4.0 times 10 to the 5th VA prime plus VA prime squared is equal to, now I'm going to replace VB prime squared with the result that I just got, which is VA squared. I already know what that is. That's the 1.6 times 10 to the 11th. So 1.6 times 10 to the 11th, and then minus VA prime squared, like that. So now we can see that this 1.6 times 10 to the 11th cancels out with this 1.6 times 10 to the 11th. And what we see is, I'm going to go ahead and steal this and put it on the next page. I'm going to say copy. And now I'm going to say paste. That's what we got. We can ignore some of the stuff along the top. I'm going to do that just so we don't get confused what's going on up here. Okay, so now that we've gotten rid of that, we can now say that negative 4.0 times 10 to the 5th VA prime, pulling the VA prime that's negative on the right to the left-hand side gives me 2 VA prime squared, and that's all equal to 0. That means we can factor out a VA prime, and then we will have negative 4.0 times 10 to the 5th plus 2 times VA prime is equal to 0. The results for that are VA prime equals 0 or VA prime is equal to 4.0 times 10 to the fifth over 2, which is 2.0 times 10 to the fifth meters per second. Obviously, that's the right answer, not the zero one. So now we have VA prime, and I can use this expression right here that we found, excuse me, this one right here that we found for VB prime. I can use that now. So I can say VB prime is equal to VA squared minus VA prime squared. So this is going to give us VB prime, and this is squared by the way, is equal to 4.0 times 10 to the fifth squared minus 2.0 times 10 to the fifth squared. This is going to give me 1.6 times 10 to the 11th minus 4.0 times 10 to the fifth, or excuse me, 10 to the 10th, like that. So 4 times 10 to the fifth squared minus 2 times 10 to the fifth squared gives me 1.2 times 10 to the fifth, or excuse me, 1.2 times 10 to the 11th. So VB prime is equal to the square root of 1.2 times 10 to the 11th meters squared per second squared. I'm going to choose the positive for obvious reasons. So when I take the square root of that, I get 3.464 times 10 to the fifth meters per second with two extra sig figs. So now I can say that VB prime is equal to 3.5 times 10 to the fifth meters per second. I've got VB prime. Now all I have to do is find theta B prime. Probably the best place to do that is to plug it into equation 1 prime. So let's plug this in. Equation 1 prime. Let's copy equation 1 prime wherever the heck that went. That looks like it's right here. So I'm going to take this number and say copy. And now I'm going to say paste. And that looks like I got everything with a little bit of extra stuff, but not anything extra that causes any problems. So now what I can do is say, I don't know where the zero came from. All right. Now what I can say is 0.75 times VA prime we found was 2.0 times 10 to the fifth. I'm going to square that. VB prime we found was 3.464 times 10 to the fifth. I'm going to square that and say that sine squared theta B prime is going to have to be given such that theta B prime is equal to the inverse sine of, and in fact, what we're going to have to do is take the square root of it, but it's the inverse sine of 0.75 times 2.0 times 10 to the fifth divided by 3.464 times 10 to the fifth squared. Oh, and this was squared too. So I'll put all that in there, and then I'll take the square root of all that. So I'm going to take 0.75 times 2 times 10 to the fifth squared. That's 3 times 10 to the 10th. I'm going to divide that by 3.464 times 10 to the fifth squared. And that's going to give me the square root of the inverse sine of 0.25. Okay. And we can tell, actually, the square root part is, so basically what we discovered is the square of the sine is 0.25, and that means sine theta has to be equal to plus or minus 30 degrees. Therefore, we choose theta b prime, which is what this is supposed to be anyways. Theta b prime is equal to negative 30 degrees. And that shows us that exactly what I predicted. The two angles have to add up to give you 90. And that's what happened. Anybody have any questions on that? All right, now class is actually over. You guys are, of course, free to go. I am going to make one more video on the center of mass stuff. I'll make that probably tomorrow, and that'll just be an addendum to this class. It'll be probably a couple examples. I'll explain the formula and explain the integral formula to you in that video, and then I'll do a couple examples, and that will finish us up with chapter 9, and we'll begin chapter 10. In fact, my intent might be to actually do some videos for chapter 10 over the weekend. So please subscribe to my YouTube channel, at least long enough for the rest of the semester, because I'm going to be popping videos up and I really want you to watch them either way, because I've got to try to make up some lost time we had. So I'm going to try to cover a little bit more material. I really need to get through chapters 10, 11, and then 14 and 15. Or it's 13, yeah, it's 14 and 15. So in order to do that, I'm going to have to give a little bit of extra time in videos that you can watch, and then obviously I'll be available for office hours to ask questions, or every time we actually meet, you can ask me questions. So you guys are free to go. I know I had a couple students that wanted to ask me questions. If you're in a rush and you can't ask me the questions, feel free to text them to me, and I will respond as soon as I can. If it requires more than just a talking or a text message, I might make a video or set up a Zoom meeting or whatever. So, you folks can go ahead and cruise. I think everybody already chatted me your first and last name. If you haven't, please do. But if you have, you're free to go. And thanks again, everybody. Thanks for coming, everyone. James, you had a question. Is this something I need to mute the system for so that this is not a public discussion, or is it a question you can ask in public?
Um, doesn't really matter to me. You can keep
I'll
it
go ahead and
muted.
stop it. If there's any question at all, that's better. So what I'm going to do is first off, I'm going to stop sharing, and I'm going to go ahead and end the recording, and we can still
Right,
talk. All right, let me just
right.
pause the recording. That'd be best.